If you are preparing for the SSC JE CB2, the second computer-based paper of the Staff Selection Commission Junior Engineer exam, there is one specific page in the Structural Steel Code that you absolutely must master. Table 3 of the IS 800 manual is widely considered the highest stakes trap on the test. At first glance, it looks like just 6 straightforward numbers, but examiners use highly specific wording in the question prompts to induce panic and force wrong answers under the ticking clock. To beat the trap, you need to understand the physics of the effective slenderness ratio, represented by the Greek letter lambda. The formula is lambda equals KL over R. KL represents the effective length of the member, and R is the radius of gyration, which is a property that measures how a cross-section's area is distributed around its axes. Physically, this ratio tells us how easily a structural column buckles or bends outward when a heavy load pushes down from the top. The golden rule of this entire table is based entirely on that physical behavior. If a member is pulled in tension, it naturally stays perfectly straight, so the engineering code allows a much higher, looser slenderness ratio. But the moment you introduce compression, that downward pushing force, the limits become extremely strict to prevent sudden structural failure. This table lays out those exact limits based on the type of stress. Looking right at the first row, we see the baseline rule. For any standard compression member carrying a dead load and an imposed live load, the maximum slenderness ratio is heavily restricted to 180. Trying to memorize the rest of these rows word by word will cost you points. To survive the exam, you have to read the table as a sliding scale of physical risk, moving from highly dangerous pure compression down to highly safe pure tension. This brings us to the first major trap the test writers set. What limit applies to a structural piece designed for pulling, a tension member, that suddenly gets pushed into compression? Most test takers spot the word tension in the question prompt and immediately guess a high, lenient number, like 350 or 400. But row 2 reveals the catch. If that sudden reversal of stress is caused by standard dynamic loads, meaning anything other than wind or seismic forces, the allowable limit aggressively snaps right back down to that strict baseline of 180. Think about the physical reality here. If a heavy overhead crane moves across a factory floor and suddenly shoves a tension rod into compression, that rod faces a severe, immediate risk of buckling, exactly like a standard load-bearing pillar. In the examiner's matrix, unexpected compression from daily operations is treated with zero leniency. It binds that tension member directly to the 180 rule. Let's shift away from the factory floor and look up at a real-world industrial roof truss system. Within this framework, you have a specific member acting as a tie or a brace. Its main job is tension, but what if a massive storm hits and pushes it temporarily into compression? The code actually gives you an exception for this specific scenario. If that compressive push is strictly caused by the action of wind or earthquake forces, the limit is relaxed all the way up to 350. The engineering logic makes perfect sense. A severe gust of wind or a seismic tremor is a transient, temporary event. Since the tie's everyday job is safely pulling in tension, the code allows it to be much more slender. This is the exact distinction that saves your score. A stress reversal from normal heavy machinery strictly limits you to 180, but a stress reversal from a temporary windstorm in a roof tie safely allows a 350 ratio. Now let's look at the absolute safest physical state in structural engineering. We're talking about members that are constantly pulled in tension, where the risk of buckling drops entirely to zero. For these pure tension components, the code assigns a maximum limit of 400, but examiners love to test the absolute edges of the rulebook, and 400 is not actually the highest structural allowance. If you look closely at the footnote hidden at the bottom of the table, you'll find the ultimate trick, the zero rule. It states that pre-tensioned members need not satisfy the maximum slenderness ratio limits at all. A pre-tensioned member is something like a sag rod, a steel rod used to align and support roof framing that is mechanically tightened during installation. Because engineers forcefully lock it into a permanently taut state, there is absolutely no risk of it ever sagging or buckling. So while standard pure tension caps out at 400, a specifically pre-tensioned member essentially has an infinite allowance. Falling for that trap will immediately separate the top-tier students from the rest of the pack. Let's sprint through a rapid-fire review to lock these 3 extreme traps into your memory for exam day. Rule number 1. Standard compression and tension members dealing with non-wind stress reversals are extremely dangerous. They share the strictest limit of 180. Rule number 2. A roof truss tie facing a brief, transient wind or seismic stress reversal gets leniency from the code, bumping the limit to 350. Rule number 3. Pure tension caps out at 400, but pre-tension sag rods dodged rules completely with no limit at all. By tying these seemingly random numbers to their actual physical behaviors under load, you've dismantled the examiner's trap matrix. You are ready to secure those points.